Hi, and welcome back to the Informatics 2 course, and we're going to start lesson 6. In this lesson, we're going to talk about sorting, ordering data. In this lesson, we're going to talk about why to sort data, and we're going to divide the sorting techniques into what's so-called external and internal techniques or algorithms. And then we're going to talk about some of these algorithms. We're not going to talk about all existing algorithms for sorting data, but rather we're going to focus on some of these algorithms, and we're going to see this as we move on. Basically, in this lesson, we're going to cover the insertion sort algorithm, and in the coming few classes, we're going to talk about other techniques. Okay, let's start. Why sorting? Well, as we all know, the world is obsessed with keeping information of any type. Could be names, could be numbers, could be anything actually. And the world is full of this kind of information. And now, if that is the case, then if someone wants to refer to any piece of information, to any data, then there has to be some way of putting this data together in some sort of order fashion, sensible order, so that I can refer to this piece of information easily. And that's why we have to sort somehow this data. So sorting algorithms are mainly of two categories, two major types. The first is what's so-called external or internal. What is the difference between external and internal? Well, external sorting is when we have a huge amount of data that cannot be handled and stored all together in the main memory of the computer. So the data will be kept in external, and that's why the name external, on external storage, like files, disks, tapes, and any other means. So if the data is too huge to fit on the memory of the system, then the data is going to be kept on these secondary storage means, and then to sort it, we have to go back and forth between these devices and the main memory to be able to sort it. On the other side, when the data is of manageable size, that's the data can be kept internally in the high-speed memory, then it's definitely faster to access this kind of data. As a matter of fact, when it's loaded in the main memory, and then the algorithms are going to run much faster, and that's why these types of algorithms and techniques are called internal sorting. So based on that, we can divide the sorts into either internal, and along this internal, I have the main category of insertion sorts. Under this, there are two very well-known techniques, what's so-called insertion sort and shell sort. Or we could have what's so-called selection algorithms. Under this, there is the what's so-called selection sorting algorithm and heap sorting algorithm. Or I could have what's so-called exchange. And among these algorithms is the very well-known bubble sort algorithm and the what's so-called quick sort. All of these, as I said, are internal sorting algorithms. That means the size of data they deal with is sort of manageable and can be loaded all together in the main memory of the program. The other category is the external sorts. External, where the data is huge and it can't be loaded all together to the memory, and so it's going to be sitting on secondary storage. Among the very well-known techniques in there are the what's so-called natural sorting algorithm, balanced sorting algorithm, and polyphase. And there are, of course, many other techniques that became along the road, and researchers have done a great job along this direction. Okay, where's going to be our focus in this course? Well, our focus is going to be on the internal sorting algorithms only. We're not going to cover any of the external techniques. And in that, even for the internal sorting, we're not going to study all of them, but rather we're going to only study few, just case studies. So I selected to talk about insertion sort, and this is the major sorting technique from the insertion category. And from the selection category, I picked the selection sort, which is the mother of all others. And from the exchanged, I'm going to talk about the bubble sort. So basically, these are the three sorting algorithms that we're going to learn in this course. In today's lesson, lesson 6, I'm going to talk about the insertion sort. Actually, these algorithms, they differ in the way they handle data to get to the ordered list. And based on that, the complexity of these algorithms, the number of computations required, and the number of the time it takes for the computer to get the list done is actually the key issue in distincting between the different sorting algorithms. So then the way we're going to cover these sorting algorithms then is to first explain in details how the sorting algorithm works, and then write a typical code, C code for that, some sort of implementation for the algorithm, and then go through some very basic complexity analysis of the algorithm. Okay, so then let's start with the insertion sort. How does it work? Well, insertion sort, the very typical example on that is when you want to somehow sort your home library. Let's say you have a bookshelf and you have many books. As you go over the years, you have some, let's say, computer books. You have some literature books, something in history, something in whatever. You know, it's a collection of books. And your library is now mixed up. To get to any book, you have to search all the shelves to find it. So a better way of organizing then your bookshelf is definitely to have these books ordered somehow. Maybe according to the title of the book, maybe according to the category of the book, like computers, literature, history, music, whatever. And whatever the key, you're going to make the sorting based upon. Well, the easiest way to handle your bookshelf is to take all books off the shelf, put them on the floor, and start inserting book after the other. Well, the way this thing works, the insertion algorithm works, is that we're going to divide actually our list into two sublists. One of them is called the sorted sublist, and the other is called the unsorted. So these are already in place, ordered, and this one is still a big mess. Random. I don't know which is which. Okay, so basically, assuming this wall in here, which divides between the sorted part and the unsorted part, then I'm assuming here that I'm in the middle of the operation, and I already have like 4 elements that are already sorted, and the rest are unsorted. The way it works now is that I will look at the first entry in the unsorted list, and I want to find the proper place for it in the sorted sublist. So the easiest way to do that is to go through the elements from the very last one in the sorted down to the first one. Each time, I will compare the key in here with the key in here. In our examples, I'm going to assume always that I'm going to always sort the list in ascending order. That is, the smallest is going to be the first element, the largest is going to go to the last place. So, given that, the way the algorithm is going to go is like this. At each step of the algorithm, the element from the unsorted sublist is inserted in the proper place in the sorted sublist. And the proper is actually the key in this whole thing. We need to find it. I need to make lots of comparisons to find that proper place. Well, after I insert this new element in the sorted sublist, then obviously the unsorted list size has been reduced by 1, since that element has been migrated now to the sorted list. So the size of the unsorted list is going to be decremented by 1. And on the other side, the sorted sublist size has been increased by 1. Okay, so how to initialize then my algorithm or my program to do this? At the very beginning, I'm going to assume that the first entry is going to be placed on the shelf. The first book I get right away, without looking at any other books, I'm going to place it in the first place, and that's sorted for me. No one is bigger than it, no one is less than it so far in the sorted list. So then the initial size of the sorted sublist is going to be 1, the first entry in the list. Then obviously, if I have n elements in the list, then the size of the unsorted list is going to be n minus 1. That's the initial setting for my program. Then after that, after each pass of the algorithm, the sorted sublist size is going to get incremented as I'm inserting a new entry into this sublist. On the other hand, the unsorted sublist size is going to be decremented by 1 as I already took that element and place it in the sorted sublist. The algorithm stops, and this is the terminating condition, when the size of the unsorted sublist is 1. That means definitely this last element is going to be the very last element to look at, and then it's going to be just inserted right away to the sorted sublist. So this is basically how the algorithm goes. Let's see an example and how this thing works. We'll assume that I have this list which consists of 6 numbers, integers. They're randomly inserted in the list. So I have the smallest number coming in here, and they're just random. And now I'm going to initialize my algorithm, my sorted sublist and unsorted sublist. The first element, which is the 23 here, is going to be taken as my first entry in the sorted list. And the remaining are going to be in the unsorted sublist. Okay, I'm going to proceed now. I'm going to take this one now and place it in the proper place in the sorted list and adjust my sublists accordingly. What I'm going to do, I'm going to take the 78, compare it with the 23. It's bigger. Okay, then it comes right after it. Okay, great. Insert it here in the second place. Okay, actually it was in the second place already, so I did not move it. That's the key thing. But this wall has been advanced to here, so that these 2 elements are now sorted and these remaining 4 elements are unsorted. This is pass 1 of the algorithm. I proceed to pass 2. Pass 2, I'm going to be looking at this element now. I need to insert it in the proper place. So what I'm going to do, I'm going to compare it with this. Oh, it's smaller. So then I have to push this 78 backward to make a spot in here, and then I will insert the 45 in here. Actually, what I'm going to do, I'm not going to insert it each time I find a bigger element, but rather I'm going to keep comparing till I find the proper place. Like what I'm going to do exactly, I'm going to compare the 45 with the 78. Okay, it's smaller. Push to the right. Okay, and then compare with the 23. No, it's smaller. Okay, I'm done then. All right, so one move, empty spot is made in here, the 45 is inserted, and the 78 goes after that. The wall has moved forward, and the size of the unsorted is now bigger by 1, and the size of the unsorted is smaller by 1 element. I move forward. Step 3, the 32, compare it with this. It's smaller. Push. Compare it with this. Yes, smaller. Another push, and now with the 23. Okay, that's it. This element is smaller. So this is the proper place where this new entry has to be inserted. Then what I'm going to do is move this and this, make a spot in here, insert the 32. And that's what I get after this pass. And again, the wall has been moved forward by one element's size. Okay? And then, now I have the last element. Okay? And then I just need to find the proper place for this and terminate. 56 compared against this, smaller. Against this, no, it's bigger. So it's going to be inserted in here. And that way, I insert it now in the proper place, pushed the 78 backward to the right, one position, and that's it. The whole list is now sorted. This wall comes to the end, and I'm done with my assignment. So that's basically the insertion sort. Let's write down a piece of code which basically implements this algorithm. I'm not writing the whole program, but rather I'm just writing the piece of code which basically covers this technique. Basically, I'm gonna go all over all elements in the list, and the list, I'm assuming, is some sort of an array of integer for simplicity. It can be of anything, as a matter of fact. So I'm gonna go all over all elements, except the last one, of course, because I said we're gonna stop when the size of the unsorted list is 1. And that means I'm gonna go through n-1 elements. All right, so I'm gonna start from I equals 1 to n-1, and that's where I stop. And I go to the next element each time. What am I gonna do? Well, what I'm gonna do is I'm gonna compare the current element, which is the top element in the unsorted list. Okay, so this is the ith element, if you like. Here's my list, something like this, and it's divided into sorted and unsorted. I'm at element I. This is the wall which separates the sorted from the unsorted. Okay, so this is the ith element in the list now. This is element I-1, I-2, I-3, down to 0. So what I'm going to do, then, I'm going to compare this with the previous one. And if it's smaller, then I have to push, right? So let's see how we do that. So if array of I, the current element, is less than the last element in the unsorted list, which comes right before it, then what I'm going to do, I'm going to save this current element in a temporary location called value. Okay, I'm going to put it aside, all right, to see where to put it in the final position, in the final correct position. And then I need to see if I need to go backward any further. So to do that, I'm going to then start from this last position in the sorted sublist down to 0 to the first entry in the sorted list, okay, decrementing each time, so it's like going backward in here. Each time, what I'm gonna do, I'm just gonna push these elements to the right, okay? So I'm making this assignment then. Make the next entry equals to this entry. So basically what I'm doing in here is if this element comes to be smaller, as it says, then I need to move this one to here, move this one to here, this one to here, okay? As long as I need to make that move, as long as the ith element comes to be smaller than these elements we're talking about in here. So I'm pushing then to the right, if you like, okay? And each time I'm gonna check if the entry in hand, okay, is less than value. Well, if this entry in here becomes less than the ith element, then I have to stop, okay? Or if I have reached the beginning of the list, so no more elements to move. In both cases, when I find an element which is smaller than the element in hand, or I reach the beginning of the list, then I have to stop. So what I do, I break. Okay? Now elements have been moved till I found the proper place, and then now the proper place is empty. Okay, so what I'm going to do, I'm going to make an assignment. Put in this location, now the empty location which I reached at, put this entry, the ith element, which I already saved in here. Okay, so I'm not going to make assignment. I'm not going to place the book in the proper place unless I find that proper place. So I keep making comparisons, moving objects accordingly till I find the proper place. And then I end my code. I end the process. Okay, so this basically covers the insertion sort. Okay? Let's look at the complexity analysis now. Let's see how many comparisons, how many insertions or assignments I have made, because that's actually the key issue in determining whether I should use this sorting algorithm or another sorting algorithm. The goal is to have the term best sorting algorithm. That means the algorithm which runs faster, which uses computer the list. That means less number of comparisons, less number of assignments. Okay, let's see how that works. Here's my list, okay? And I'm talking about the ith element in here, and I want to move it backward to the proper place in the sorted sublist. So on average, how far should we go back to insert the ith element in the right position? Well, that depends. Depends how big or small the element in hand is. Okay? So the element in hand could be the biggest as compared to the sorted elements. In that way, I'm not going to go back at all. Or I could go back one step, two steps, all right? Or at most, I could go, this is the ith element, remember? So I could go back to insert it in the first place because it happens to be the smallest. In that case, I went back I minus 1 positions. So these are in general, I possible scenarios, either 0, 1, 2, 3, and up to I minus 1. Okay? These are the possible scenarios. Well, here's what we're talking about. That's the main loop, the outer loop. I'm going around all elements. And for each element now, I'm going to compare it with the previous one. So it could be already bigger, then I stop, no go backs. Or I could need to go more than just one step or two steps or three and so forth. And then if I do that, I have to get into the inner loop which performs these comparisons. So this is called the outer loop. In this outer loop, as we can see, okay, there is a comparison that I make. Okay? I compare if this less than that. This is called comparison. No assignments. No entry has been assigned a value. Okay? So one comparison, 0 assignments in the outer loop. Okay. And this basically talks about how far we should go back. Possible scenarios, as I said, in the outer loop is either 0, 1, up to I minus 1. Case 0, we're going to call it no go back because the element in hand, the ith element, is actually the biggest amongst these elements in the sorted sublist. And that's why I'm not going to go back any position. Or I could go 1, 2 to I minus 1 possible positions backward, and in that case, I need to get into the inner loop of the code. Well, on average, I could either go back 1, 2, 3, 4, and so forth. That's why we calculate the average of going back to be the sum of all these possible scenarios divided by the total number of these scenarios. Total number of these scenarios is I minus 1, and the sum is simply 1 plus 2 plus 3 plus up to I minus 1. if we make the calculation in here, and it's simple, straightforward, then this average comes to I divided by 2. And this is logic. Actually, the size of this sorted list is I elements. It contains elements from 0 to I minus 1. So on average, I'm going to go back half that distance. Okay? So this is straightforward. In the case of no go back, inner loop is skipped. I'm not going to go back at all. Hence, one comparison, 0 assignments. That's the total number of comparisons and assignments for that particular entry. Case of go back, the inner loop is going to be executed because I need to find where is the proper place. And here it is again. Well, let's look into it. What do I have in here? I have an assignment at the very beginning, and then I have a comparison. Okay, one comparison, one assignment. And there is an assignment down here outside the loop. Okay, so inside the loop, I have an assignment and I have a comparison, and there is an assignment outside, of course, and there is another assignment before this. Okay, just remember these facts. This is the inner loop. Average number of iterations. This depends on how far I need to go back. I don't know, it depends upon the number in hand, definitely. So again, we're going to be talking about average number of go-backs. Well, again, the average number of go-backs is either 1, 2, or I minus 1. The average is, again, the sum of all of these possible scenarios divided by the total number of the scenarios. And again, it's I over 2, half the distance. Comparisons and assignments. At each iteration in the inner loop, what do? One key assignment, that's the very beginning when I put the ith element in value, the temporary storage. And then one key comparison to see if I need to go back or not. That's inside the for loop. And furthermore, there is one outside this loop. There are 2 assignments. Okay? And these 2 assignments are, let me go back real quick. Here it is. One assignment and one comparison inside the loop. And there are 2 assignments outside the loop. That's what I'm referring to. Okay, I'm trying to go a little bit fast here. Okay, so one assignment, one comparison inside the loop, and there are 2 assignments outside the loop. And there's one key comparison. That's at the very beginning. Hence, entry I requires an average of I divided by 2 plus 1 comparisons. That's the average which we just calculated, plus this outside the loop. And number of assignments is actually I divided by 2 as an average, plus 2 outside the loop. That's just for one entry in the array. Now assume that my array is random, where elements could be anything, and then we're going to assume furthermore that the probability of occurrence of any entry is equiprobable. That means any entry could be in any location at the same exact probability. So if I have, if you like, I elements in there, then the possibility of having any entry is simply 1 over I, like tossing a coin. It's either a head or a tail. Probability is the same for the head or the tail. So it's 1/2, 1/2. 1 over the total number of possibilities, 1 over I. That is, the probability of having the event of 0, that's going back 0 times, equals the probability of going back once, twice, 3 times, or I minus 1 times. And in all scenarios, in all cases, this probability is simply 1 over I, 1 over the total number of possibilities. Then, based on this, the probability of no go back, which means the probability of 0, is 1 over I. On the other hand, the probability of going back, and now going back could be 1 position, 2 positions, I minus 1 positions, then in that case, it's 1 minus this. The total probability, which is always 1, minus this. So either I go back or I don't go back. Simply. Therefore, combining the two cases together with respect to their probabilities, I will get this result. Number of comparisons equals 1 over I, that's the probability of occurrence of no go back, times 1. I go back in that scenario is just one case. Or the probability of going back, okay, which is the 1 minus 1 over I, it's just rewritten in here, times the number of comparisons, which are I over 2 plus 1, as we have mentioned earlier. So the total in here is simply I plus 1 divided by 2. And number of assignments, again, possibility of no going back, 1 over I, times 0, no assignments whatsoever, as I said, in the outer loop, plus the inner loop. Probability is I minus 1 divided by I, times the number of assignments I make in there. So the average is I over 2 plus 2, as we mentioned earlier. So this comes to this expression, I plus 1 divided by 2 minus 1 over I. Well, there is the big O notation, and we're going to talk about this later on in this course. However, what it says, instead of looking at all the details of the expressions, we just want to look at the order number of computations. So we here concentrate on the major factor, on the major term in the expression. So if I want to use the big O notation, then to put the expression for the number of comparisons, then it's going to be the major factor is I over t plus order of 1, order of constant. And number of assignments is again I over 2 plus order of constant. This is the major driving factor in the expression which we just derived. Okay? Well, so far the analysis covers only one element in the list. Now we want to generalize this to all n entries in the list. So if I want to do that, then the total number of comparisons, okay, equals to the total number of assignments, actually, when I talk about the big O notation, because as we said in here, they're the same, okay? They only differ in this least significant term. So based on that, then the total number of comparisons is going to be the sum of the number of comparisons for one entry, and I'm going to generalize this for all entries. So the sum is going to go from I equals 1 to n, all entries in the list. And if I do this, this is a simple geometric series, and it comes out to something like 1/4 n squared plus order of n. And that means if I have a list of n entries, then on the average, I need a number of computations, comparisons, and assignments in the order of 1/4 of n squared. So for example, in the order of, if I'm talking about something like 100 entries in my list, then the total number of comparisons or computations, I'm gonna call them, is in the order of n squared divided by 4, 10,000 divided by 4, in the order of this, okay, plus order of 100. That's what we're saying in here, okay? Advantages and disadvantages of this algorithm. Pros or advantages. It's very simple to understand and implement. Easy, straightforward. Fill in your bookshelf with books. So basically, you're in the middle of the process. You pick a book from the floor, and you look at the books that you already have on the shelf, okay? And then you're gonna start moving aside the books according to whatever book you have in hand till you find the proper place and place it in there. Straightforward, very logical, and very simple. However, I have a problem in that I don't know where to put the element in hand in the proper place. So if the books are already sorted, sort of semi-sorted, then hopefully I'm not going to go back that far, because the major driving thing, actually what makes more computations, is when I need to go into the inner loop, and that's where I need to go back in the sorted list. So if my list is semi-sorted, then hopefully I'm not going to be going back that much. All right? And I could go back only once or twice at most. So if that is the case, then definitely this is an excellent choice to sort your data. Okay? And then I'm going to have a number of computations definitely less than this number. Again, this number was average number, assuming for randomness of the data. It could be less, it could be more. Okay? So if the data is sort of sorted, then the number of comparisons are definitely going to be less. Disadvantages? Well, a no element may require many moves even when array is sorted. Oh, and that's a problem. I don't know. I could be the unluckiest person in the world, and I already have 100 books already sorted in my sorted sublist. I picked a book, and it's the smallest according to the key. So I need to move all the books that are already on the shelf backward to make a slot to where I need to put this no entry. And this is a problem, of course. Okay? So I can never tell where to insert the no element. All right? Because simply, assuming for randomness, that entry could go anywhere in the sorted list. And this is actually a disadvantage because I can never tell where to go and how far to go. The second thing, actually, is the proper position of the element. I can never know and guarantee that this element, which I already put in proper place, all right, is going to stay there for the rest of the process. Because simply, yes, now this is the proper place for this element, but God knows whether that place is going to be its final place or not, because simply another entry is going to come later on, and I realize that I need to move this entry backward because this entry is simply smaller, and that needs to go to this position. So none of the entries in the list will go to its final position until I'm done with all entries in the list. And this is a sort of disadvantage because I can't count on the position till I'm through with the rest of the elements in the list. Actually, we move one position at a time. And this makes it a little bit slow. I can't make big jumps or chunks of jumps, and simply because I need to check with every element, because simply the element in hand could fit anywhere in between, so I have to be very careful. That's very much covers the insertion sort algorithm. Hope you liked it. I would like you to try this on your computer. If you need to look at more examples, exercises, with regard to the sorting algorithm, then I definitely encourage you to go to the internet, to the UNINETTUNO website, and click on the MidNetU project, and you're going to find all the material you might like. Thank you very much. I'll see you next time.